Morning, everyone. How's everybody going? How's everybody doing? Questions while we're waiting for people to come in? Morning, everyone. Come on in. Any questions in the meantime? Andre, I don't know what the first WebWork question is. Can you tell us what it is? Morning, everyone. Finding the inverse of 3x cubed plus 8x plus 3. That is not something we are responsible for. You can show, we'll be able to show easily that this does have an inverse. Solving for the inverse, though, is not immediately clear. Andre, we considered that question last time. So if you look at the last video, we essentially did that question in class. Kamal, send me an email. And you're not the first person to suggest that. I'm going to email the survey people to make sure that the word is included at the end. Aaron is asking if arcsine of sine 5 pi over 4 is negative pi over 4. Sounds correct, yes. Man, see that is all right, moving on. How are we doing? Questions? We're good? Let's go back to, well, people, let's stop giving the answer. The point is for you to actually do the survey, because it's important for the people doing the research. It's a survey on online learning, and I mean they're doing important work there. So please fill out the survey. The word may change depending on, right? Because I mean, the same with web work, but yeah. There is no handing in of anything, Noah. Web work is done online. I mean, apart from the exams, that's all there is. The survey is the last question on the web work. All right, let's move on. Let's move on to what we were doing last time. Namely, we introduced the concept of limit. And let's recall the definition. When is our first exam? I believe we have set a date. I'm gonna have to look at the email again, but I think it is Friday, October 23rd. I think that is the day of the midterm. It's going to be a 72-hour midterm, so it's going to be released on that day. You'll have 72 hours to complete and submit the exam. But an announcement will be made on my courses, but I think it's October 23rd. Well, I mean, those people who didn't see the word, please email me. How hard will it be? If you're comfortable with the material, it's going to be very easy. If you're not comfortable, yeah. All right. We introduced the definition last time. The concept of limit. What did we say? We said that limit as x goes to a of f of x is L if f can be made arbitrarily close, close to L by taking x sufficiently close to A. If you're doing Stewart and you're comfortable, that's where you need to be. I don't think it's going to be much harder than that. Keep in mind, though, that the questions might be more conceptual in nature, only because if I ask you to evaluate a limit, you have a bunch of tools that you could use. In particular, Wolfram Alpha is going to evaluate limits for you. So, we are trying to stay away from questions that are immediately answerable by Wolfram Alpha. Thank you. That's a very important, Jennifer, thank you. It's a very important condition. Sufficiently close to A, but not equal to A. Right? So, in other words, the limit is the behavior of the function. What we're saying here is that the function f is very close to L if you take values of x very close to A. That's what we're saying. The function behaves like the number L. And once we had understood this, we actually took it a step further and we defined left and right-handed limits. We defined limit as x goes to A from the right and limit as x goes to A from the left. In a similar fashion, right, by either restricting our attention to numbers bigger than A or numbers less than A. And of course, this led us to the realization that a limit exists if and only if limit from the right and limit from the left both exist and are both the same. Let's take some exercises from the book. All right, so suppose that this is the graph of a function f of x. Is it possible to have a right-handed limit when approaching infinity? Well, even though we haven't discussed limits as x goes to infinity, the answer is no. There's only one way to go to positive infinity, and it's this way. All right, consider this function. Here are some questions. Limit, what is the limit as x goes to 2 from the left? How does the function behave as x goes to 2 from numbers less than 2? So as you're going towards 2, what is happening to the function? Function is getting closer and closer to 3. There it is. What about limit as x goes to 2 from the right? As you are getting closer and closer to 2 from numbers bigger than 2, what is happening to your function? Function is getting closer and closer to 1. Very nice. What can we say about the limit as x goes to 2 in that case? Limit from the left is 3, limit from the right is 1. The limit as x goes to 2 does not exist. Right? These two things do not agree. The limit itself does not exist. What is f of 2? F of 2 is 3. Absolutely. Right? This has nothing to do with limits. What about limit as x goes to 4 from the left? What is happening as the function right? Function is going towards 4. Limit as x goes to 4 from the right. So we're going towards 4 from the right. What is happening to the function? Getting closer and closer to 4 as well. Absolutely. What about limit as x goes to 4? Michael is suggesting does not exist. Other people are saying 4. What is Riley is asking, what do the plus and minus signs mean? Well, somebody want to address that while we're here? The answer is 4. What do the plus and minus signs mean here for Riley? They are left and right-handed limits, meaning you are restricting your attention to numbers less than 4 and numbers bigger than 4, respectively. Absolutely. One last thing, one last question here. What is f of 4? Here, f of 4 does not exist, or f of 4 is undefined. Absolutely. Very good. Let's try another one. All right. Again, this is your function f of x. All right, same thing. All right, same kind of questions. My question to you is, what is the behavior as you are approaching -3 from the left? All right, what is the behavior of the function as you are going to -3, but from the left? Function is getting closer and closer to 4. Exactly that. What about the limit from the right? So -3 from the right. Same thing, right? What is the behavior of the function as you are getting closer and closer to -3, but from values bigger than -3? Of course, the answer is 4. It's immediate from the graph, right? So what is the limit as x goes to -3? Limit from the left and the limit from the right both agree. So the limit itself exists and is 4. Absolutely. What about f of -3 though? Right, undefined. Undefined or does not exist. Absolutely. And you know, this brings up, let me address that point. This brings up the fact that the limit itself is not affected by what the function is at -3. Right? This is immaterial as far as the limit is concerned. Here, the function isn't even defined at -3. And people are asking why. Well, I mean, you've got this open point here at -3. We don't know what the function is at -3. In fact, it's not even defined at -3. But that doesn't matter as far as the limit is concerned, because the limit is the behavior of the function very close to -3, but not at -3, right? In the definition of the limit, it's by taking x sufficiently close to a, but not equal to a. And that's the whole point. It doesn't really matter what the function is at -3. It's how the function behaves very close to -3. But not exactly at -3. Let's repeat with 0. What is the limit as x goes to 0 from the left? Well, the limit approaching -3, we have it right here. Right, so there it is. And Benjamin is asking, would a derivative exist at, I assume you mean -3, even though we haven't defined, Benjamin, yes, he made that correction. We haven't defined the concept of derivative yet, but the answer is no. The answer is no. One big reason being that you need, well, I mean, first of all, -3 isn't even in the domain of the function, right? Your function is not defined at -3. So it's not even on the radar. So we can't talk about anything occurring at -3. -3 is not defined. That's the first big issue. As people are suggesting, there's some sort of cusp happening. It's not continuous. So all of these are many reasons for which the derivative, this function is not differentiable at -3. But for those of you who've never seen the derivative before, don't worry about it. We're not there yet, but we're getting there. Now we're just talking about limits, though. What is the limit as x goes to 0 from the left? So as you are getting closer and closer to 0, from numbers less than 0, what is happening to the function? Getting closer and closer to 1. Exactly that. What about limit as x goes to 0 from the right? From numbers larger than 0. Right, as you are getting closer and closer to 0 from the right, the function is getting closer and closer to -1. Thank you. What can you say about the limit as x goes to 0? This does not exist. Precisely that, right? The limit from the right and limit from the left are different. They're not equal. The limit itself does not exist. What about f of 0? F of 0 is 1. Thank you, Joanna. What if we ask for a limit as x goes to 2? I'm not going to break it up into left and right-handed limits. You could if you wanted to. When we state that the limit does not exist, do we need to give a reason why? Well, I mean, you could, right? Here, limit does not exist since limit from the left and limit from the right are different. So that's fine. And people are giving me a limit here of 2, and that's exactly correct. Why not -1? For what? For f of 0? F of 0, right? Here at -1, you've got a hole, meaning it's not that, but it's this, because you've got the dot right there. So that's why it's 1 and not -1. Limit as x goes to 2 is 2. We did not need to split it up into left and right-handed limits because we know exactly what's happening. You could if you wanted to, nothing wrong with that. Limit from the left would have been 2. Limit from the right would have been 2. Consequently, the limit would have existed and have been 2, exactly as we suggested. Can we use undefined and does not exist interchangeably? Let's not. No, because does not exist is kind of different from undefined, right? If limit approaching 5 from the left does not exist since it's oscillating, absolutely, right? I mean, that is, of course, our following question. What is the limit as x goes to 5 from the left? And you see that the function keeps oscillating as you approach 5 without actually going towards one specific number. So this limit, even though it's just a left-handed limit, this limit itself does not exist. Gloria is asking, when do we use does not exist and undefined? Well, undefined means it is not defined. Here, if we are looking at f of -3, the function of -3 has not been defined. So we use undefined. A limit that does not exist, meaning it's not going towards one specific value. So let's say it does not exist for limits and undefined for functions. Let's use that as a rule. Why is J does not exist? Well, again, you want to describe the behavior of the function as x is getting closer and closer to 5, but from numbers less than 5. A limit, we are expecting one unique value. Is the function getting closer and closer to one value? Well, here, as you get closer and closer to 5, the function is oscillating faster and faster between, let's say, 2 and 4. So the limit, the function isn't getting closer and closer to one single number, but rather oscillating faster and faster. Can a limit ever be undefined? We usually reserve the term does not exist for limit, undefined for functions. All right. Is everybody with us here? So limit as x goes to 5 from the left does not exist. Limit as x goes to 5 from the right, I mean, it seems to be halfway, right? Let's call it halfway. Limit from the right is 3. There it is. Questions? How are we doing? Moving on. Let's move on. Let's move on to a definition. Definition. Let f of x be a function defined near a except possibly we say the limit as x goes to a of f of x is infinity. Why would the limit approaching 5 from the right be 3? Well, I mean, you should have asked me that before I erased it. But from 5 onwards, we had something like this. So if you're looking at the limit as x goes to 5 from the right, the function was getting a lot closer and closer to 3. we say the limit as x goes to a of f of x is infinity if f of x can be made arbitrarily large by taking x sufficiently close to a, but not equal to a. Near, the word is near. Are you talking about an asymptote? Well, thank you for bringing that up. Exactly that. Let me, before we introduce that word, let us say limit as x goes to a from the right. Well, wait. Limit as x goes to a is negative infinity. Similarly, right? I'm not going to rewrite the whole thing. What does it mean? It means that f of x can be made arbitrarily large negative by taking x sufficiently close to a, but not equal to a. And this, of course, extends to left and right-handed limits. So this extends to left and right-handed limits. And in this case, so let's introduce the idea of vertical asymptotes. The line x equals a is called the vertical asymptote of f of x if one of the following, well, if at least one of the following occur. Limit as x goes to a from the left is infinity, or limit as x goes to a from the left is negative infinity, or limit as x goes to a from the right is infinity, or limit as x goes to a from the left, from the right, is negative infinity. So if one of the limits from the left or right is some sort of infinity, then the line is called a vertical asymptote. Let's take an example. Let's take an example from a graph. Right? I mean, it's easy to see what is happening if you have a graph. All right. Suppose you had this function. All right. So here's my question to you. What is the limit as x goes to -3 from the left? What is happening to the function as x goes to -3 from the left? Function is getting larger and larger, going to positive infinity. Right away, without doing anything else, immediately, -3, x equals -3 is a vertical asymptote. That's it. You don't have to do anything else. As soon as one limit is some sort of infinity, that's it. So right away you could conclude x equals -3 is a vertical asymptote. What about limit as x goes to -3 from the right? What is happening to the function as you're getting closer and closer to -3, but from values bigger than -3? Again, the function is going to infinity. What can you say about the limit as x goes to -3 in that case? Both limits from the left and from the right exist and are positive infinity. So the limit itself is positive infinity. What about limit as x goes to -1 from the left? You see what's happening? As you are getting closer and closer to -1, the function is getting closer and closer to negative infinity, absolutely. What about the behavior of the function as x gets closer and closer to -1, but from the right? You see it, right? We can read off the behavior. getting closer and closer to negative infinity. What about the limit as x goes to -1? Both left and right-hand limits exist and are equal. The limit itself, therefore, exists and is equal to negative infinity. What about limit as x goes to 2 from the left? Right, again, we see the behavior. Function is going to negative infinity. What about limit as x goes to 2 from the right? Right, as you're getting closer and closer to 2 from the right, function is blowing up to positive infinity. And finally, what can you say about the limit as x goes to 2? Does not exist. The limit from the left and limit from the right are not equal. The limit itself does not exist. Absolutely. Questions? Well, let's now do the opposite. What if you were given an actual function and, well, right, I mean, Jenny, that question obviously comes up. Will we be given a graph? The answer, of course, is no. Given a graph, you can read off the behavior. It's very easy to understand the behavior from a graph. We want to do the opposite. We want to start with a function and be able to understand the behavior so that we can possibly graph it. And let's start with an important example. Limit 1 over x as x goes to 0. Let's understand the behavior of this function. I mean, perhaps you know the graph, so you might already know the behavior, but let's not make use of that. Rather, let's understand the behavior by plugging in some values of x that are getting closer and closer to 0 so that we understand what is happening to this function. Right? If we took a number close to 0, let's take 1 over 10. 1 over 10 is small, right? I mean, you see what happens. 0 is here, 1 over 10. And if we plug in 1 over 10 into this function, you get 1 divided by 1 over 10. 1 divided by 1 over 10, which is the same as multiplying by the reciprocal. Which is the same as multiplying by the reciprocal, which is 10. So at 1 over 10, you've already got a rather large number, which is 10. What if you took something closer, like 1 over 100? 1 over 100 is going to be closer to 0. And what happens? Now you get 100. And if you keep taking values that are closer and closer to 0, you see what's happening, right? The closer the value you take, closer to 0, the value you take, the larger the number actually is. And consequently, we say that the limit is infinity. Let's repeat, but looking at values close to 0, but less than 0. What happens if you plug in small fractions? Numbers close to 0, but negative. Right? So you get 1 divided by minus 1 over 100. Or 1 divided by minus 1 over 100. We're going to multiply by the reciprocal. And you get minus 100. And if you repeat, if you take something closer, like maybe 1 over, maybe negative 1 over 1,000, well, you see what's happening, right? Get negative 1,000, and so on and so on. And I think you see the behavior, what is happening as x goes to 0 from the left. This function is approaching negative infinity. Large negative numbers, I don't know that we want to introduce that terminology. Let's stay away from that. Large negative numbers or large positive numbers. I mean, you understand the idea, and there it is. And this idea, right? So, I mean, look, if you were to simply plug in 0, right? If you were to simply plug in 0, what would you get? You would get a 1 over 0 here. And if you were to plug in 0, you'd get a 1 over 0 here. So this brings up the interesting idea. This can be generalized in the context of limits. Right? Because in general, as Michael suggests, a 1 over 0 is undefined. But in the context of limits, a 1 over 0, right? Because you're getting closer and closer to 0 without actually ever reaching it. So in the context of limits, a 1 over 0 is actually some sort of infinity. We just have to decide which one. Of course, you want to be careful, right? Because if we put these two together, what can we say about the limit as x goes to 0 of 1 over x? Limit from the right is infinity, limit from the left is negative infinity, so the limit itself does not exist. Exactly that. Let's consider an example taken from the book. We are asked to evaluate the limit as x goes to 5 from the negative and what is the behavior of this function? Well, if you were to blindly plug in, the numerator would be very close to 6. The denominator, however, would be 0. So in very much the same way as before, we expect some sort of infinity, right? The 6 over 0 is going to be some sort of infinity. Is it positive or is it negative? The numerator is going to be close to 6. What about the denominator? You're taking numbers less than 5 and you're subtracting 5. So a number less than 5 minus 5, this is going to be negative. Numerator is positive, so the whole thing is negative. And it looks like a 6 over 0. So negative infinity is going to be the behavior. If you're not convinced, plug in some numbers very close to 5, but less than 5. If you were to plug in 5 minus 1 over 10, your denominator would be negative 1 over 10. And you multiply by the reciprocal, and you see what's happening. And same with 5 minus 1 over 100. These numbers are getting closer and closer to 5, but are always less than 5. In the context of limits, a non-zero number over 0 is some sort of infinity by that same reasoning. Certainly. Let's do another example. Consider this. We are looking for the limit as x goes to 3 from the left of root x over x minus 3 to the 5. Now again, if we just blindly plug in, the numerator is going to be close to root 3. The denominator is going to be 0. So we have a root 3 over 0. Again, some sort of non-zero number over 0. The answer is going to be some sort of infinity. We have to determine if it's positive or negative. The numerator is positive, and here you're taking numbers less than 3. So number less than 3 minus 3 is going to be negative, and a negative number to the power of 5 is still negative. So positive over negative, answer is negative again. Again, if you're not convinced, plug in some numbers less than 3, but very close to 3, like 3 minus 1 over 10, 3 minus 1 over 100, 3 minus 1 over 1,000, and so on, right? When you subtract 3 from this, you're left with this negative number. When you raise it to the 5, it gets even smaller. But then you take the reciprocal, because you're dividing by that. It's going to be a huge negative number. Benjamin is talking about the solutions manual. Please stay away from that. It's terrible. Do not buy the solutions manual. I'll tell you why. It's a trap. It's a trap. You're going to do some exercise from the book. You're going to start on the first question, and you're going to take a moment to try it, to look at it. Then you're not going to know what to do. So you're going to go to your trusted solutions manual. They're going to show you how to do that question. And then, oh, yeah, I understand. And you're going to do the next one. You're going to stare at the question for a moment. And then you're going to look at the answer in the solutions manual. Oh, yeah. Oh, now I get it. Now I get it. And then the next one, and the next one, and the next one. You're going to always refer back to your solutions manual because it's there. The answer is there. No need to think, the answer is there. And you'll do all the questions referencing the solutions manual, and you'll have learned nothing. Absolutely nothing, and you won't know how to answer a single question. I've seen it happen over and over and over again. Reread your notes. You know, we do some exercises in class. These are very similar to the questions in the book. You should, after having reread your notes, you should be in a position to tackle the questions on your own. Don't buy the solutions manual. We're looking for the vertical asymptotes of this function. Well, Benjamin, there's no reason to fail the class now. It's too early, but now you know the trap. Put the solutions manual away. Never go back to it. You know, you do a question, the answers are in the back of the book. If you have the right answer, you're probably fine and you move on. And, you know, if you're right, you move on to the next question. If you keep getting them right, I'm going to assume that you're doing very well. If you get it wrong, try it again. If it's still wrong, move on to another question, build your confidence back up, come back to that one you keep getting wrong. That's how you should be doing exercises from the book. No solutions manual, just look at the answer in the back once it's done. Find the vertical asymptotes. What is happening? Right? I mean, most of you have understood that if we factor out an x here, what are we really looking for? We're looking for points where the limit is some sort of infinity, plus or minus infinity. And you understand that to occur when the denominator is 0, whereas the numerator is not. And the denominator is 0 at when x is 0 or 3/2. That is not a guarantee yet that these are vertical asymptotes. Because remember, vertical asymptote is when the limit from either the left or the right is some sort of infinity. So we have to test that. We have to show that the limit as x goes to 0, either from the left or from the right, is some sort of infinity. And let's see what happens here. When x is close to 0, This 2x is going to be close to 0. So this thing is going to be close to 3. This is going to be close to 1. Right? I mean, you know the graphs of these things. This is close to 1. This is close to 3. And this is close to 0. So you do have a 1 over 0 here. So you know it's some sort of infinity. Let's finish it up by asking if it's positive or negative. And numerator is positive. This is going to be close to 3. And this is numbers bigger than 0. So that's positive as well. Everything is positive. And there it is. Now you know that it's a vertical asymptote. Right? That's the definition of a vertical asymptote. As soon as the limit from either left or right is some sort of infinity, that's it. Why did we get 0 or 3 over 2? We were thinking ahead, and we wanted a 0 in the denominator, because you know, in the context of limits, a 1 over 0 is some sort of infinity. And that's what we were looking for. I'll let you repeat with 3 over 2. You can take a limit going from the right or from the left. Doesn't matter. Well, I mean, the actual limit may be different. Let's see what happens here. This is going to be close to 9 over 4 plus 1, so this is going to be positive. This is going to be close to 3 over 2, so that's going to be positive. And if you take a number bigger than 1.5 and multiply by 2, you get something bigger than 3. And 3 minus something bigger than 3 is going to be negative. Right? This is going to be very close to 0. So you've got this 1 over 0 happening again. But positive, positive, negative, the whole thing is going to go to negative infinity. Questions here? How are we doing? Let us consider some limit laws that will allow us to, can we explain why it's negative again? Let's look at these three things separately on a graph. You know the graph of this, right? It's like x squared, but just moved up by 1. And as we are getting closer and closer to 3 over 2, that function is getting closer and closer to 9 over 4 plus 1. So 13 over 4. Right? Really the only thing that's important as far as we're concerned is that it's positive in this case. You know the graph of x. And when x is close to 3 over 2, that itself is going to be close to 3 over 2. And you know the graph of 3 minus 2x. So the straight line coming down. And when it's close to 3 over 2, the function is close to 0. But if we are restricting our attention to values bigger than 3 over 2, your function is negative. So numerator is positive, this is positive, but that is negative. So the whole thing is negative. In what context would you find the zeros in the x in the denominator and have it not be an infinite limit? An excellent question, Rachel, right? Why don't we address that? But before we do, are we back? We're back. Excellent. Excellent. So let's consider some limit laws before we answer Rachel's question. Suppose that we have functions f and g where both limits as x goes to a exist. Then the limit of the sum is also going to exist. And the limit of the sum is the sum of the limits. In other words, you can distribute the limit, if you will. Limit of a sum is the sum of the limits. If c is a real number, the limit of c times a function is c times the limit. Do we have to prove these laws? No. Let's just assume them. I'll prove a few only because they're easy to see. 3, the limit of a product. Is the product of the limits. Right, Michael? Reminds you of linear transformations? Absolutely, right? I mean, the first two conditions exactly say that. The limit is linear. The limit process is linear. Absolutely. So limit of a product is the product of the limits. 4, limit of a quotient. Is the quotient of the limits provided the limit of the denominator is not 0. Five, for a bigger than or equal to 0, the limit, no, sorry, I don't want to use a. For b bigger than or equal to 0, limit as x goes to a of f of x to the power b, right? The limit of a power is the power of the limit. 6. If c is a real number, the limit of c is c. We'll prove this one. It's trivial. We'll prove this one as well. Limit as x goes to a of x is a. I think we essentially already proved that one, or at least convinced ourselves of that. And finally, one more, and that's the important one, considering Rachel's question. If f of x is equal to g of x for all x not equal to a, then the limit as x goes to a of f of x is the same as the limit of g of x. This is clear from the definition of limit, because you know a limit is the behavior of the function. It doesn't matter what is happening at x equals a. Whether or not they're equal at a doesn't matter. It's what happens near a that's important. It's the behavior for values close to a but not equal to a. So there it is. Let's prove a few. Let's prove number 6, or at least understand what's happening here. Let's prove number 6. If c is a real number, let's look at the graph of y equals c. You know what that graph is. It's just a straight line. So the question is, what is the behavior of that function? If you take values close to a, the function is close to c. In fact, the function is c. So the limit, how does this function behave near a? It's c. And that's it. Let's look at 7. And once again, you know the graph of this. Y equals x is just a straight line through the origin. And for values close to a, what is happening? First of all, this gets mapped to values close to a. And that's all this is saying. Limit as x goes to a of x is a. Conclusion. Conclusion. What is the conclusion? If we look at limit as x goes to a of x squared, one of the properties, one of the limit laws, I think it was limit law number 3, well, or limit law, the power business, right? This is the limit as x goes to a of x all squared, right? Where b is 2 here. And this is just a. So this is a squared. And you can repeat, Joanna, absolutely, right? And you can repeat limit as x goes to a of x to the n. Same process. And you get a to the n. And similarly, if c is a real number, the limit as x goes to a of cxn, well, you can pull the c out. And this we just worked out to be a to the n. So this is c times a to the n. Where am I going with this? I'm suggesting that if you start with a polynomial, then the limit of that polynomial is just p of a. Why is that? Well, what does a polynomial look like? Since a polynomial has the form bn x to the n plus bn minus 1 x to the n minus 1, and so on, where the b's are real numbers. So the limit of this, first of all, you can break it up into the sum of limits, and then you can pull out these real numbers, and this limit is just a to the n. So it's the same thing, it's substitution. Can't p of x be any function? Well, the answer is no. And the answer to that is the example to Rachel's question. Right, but before we get to that, let's do a few exercises from the book to illustrate this idea and reinforce everything. And let's not skip any steps here. Let's justify every step along the way. We are running out of time. It's all good. So first of all, here I have a limit of a sum. So by property 1, I can break this up into the limit, into the sum of the limits. This is by property 1. And now, by property 3, I can take constants out. So this is 2 times the limit as x goes to negative 3 of x cubed, plus 6 times the limit of x squared, minus the limit of 9. This is by property 2. Am I by property 2? And now, this is the property, this is the limit of x all cubed. And this is the limit of x all squared. I think that's by property 5. I'm going to let you confirm that. Right, Michael? And then this limit, you can, the limit of x as x goes to a is just a. We prove that. So this is 2 times negative 3 cubed plus times negative 3 squared. These two are by property, I want to say 7. Right, I want to say property 7 for these two and property 6 for this last one. Does 2 and 6? No, because it's not 2x all cubed, right? It's just the x that's cubed. And same for the 6. So there it is. This is 2 times negative 27 plus 6 times 9 minus 6. So that is minus 54 plus 54 minus 6. So the answer is minus 6. And what I was suggesting earlier, right? You see, if you define p of x as 2x cubed plus 6x squared minus 9, this is a polynomial. Sorry, what? Minus 9, thank you. Minus 9. Sheridan wants to know why we can get rid of the limit x from the equation. This limit we proved in property 7 that this limit was a. Here a is negative 3. So that limit is a by 7. That limit is a by 7. So we get these two. And this limit by 6, by property 6, is negative 9. And that's what I was trying to explain. If you define p of x as this, a polynomial, the limit as x goes to -3 of p of x, which is what we're looking at, is p of -3. You can actually substitute -3 in to your polynomial, right? So 2 times -3 cubed plus 6 times -3 squared minus 9. And you'll get -9. You get the answer. Can we use product and addition laws? We just went over the limits are plus or minus infinity. Sometimes yes, sometimes no. This is always true in the case of a polynomial. So in the case of a polynomial, you're fine. You can always plug in. In the case of a rational function, if you have a rational function, which is one polynomial divided by another, so if you have one polynomial divided by another, then you can do that as well. By property I want to say 4. And, well, I mean, and what is that? This is by property 4. And now this limit by that same property here, this is P of A. And this is Q of A. Q of A. As long as, I guess that should come here. As long as Q of A is not 0. Let's just do one last one so that you can get started on these exercises. Well, 1 or 2, let's say. Consider this. First of all, don't let the t fool you. Whether it's t or whether it's x, it's the same thing. Can we combine the rational function rule onto the quotient rule? Well, if you're referring to quotient rule as in derivatives, we're still very far from derivatives here. This is a 5. I understand that my 5s look like s's and vice versa. It's a 5. All right. Well, what's to notice? This is a rational function. It's one polynomial divided by another. So as long as this polynomial evaluated at 7 is not 0, we're done. And what is that? That's 49 minus 35 is what? 14 plus 2 is 16. It's not 0, that's it. We plug in 49, so that's 150 minus 3, 147, 148. Divided by, what do we say, 14? 15, 16? 148 divided by 16. There it is. Thank you, Joanna. And that's it. I mean, you could, since they're both even, you could simplify that slightly, but whatever. There it is. Since both of these are polynomials and the denominator is not 0. Let's do one last one, and that'll be it. Again, 5. And again, we're going to justify every step according to the limit laws we just erased. Here you've got the limit of a product. So by property, I want to say 3. So by property 3, the limit of a product is the product of the limits. By property, is it 5 again? The limit of a power is the power of the limits. And finally, the limit of a polynomial or rational function, maybe we'll refer to that as 1/3, thank you. That should be 1/3. Absolutely. Thank you. And why don't we give it a name? Property 10, the limit of a polynomial is P of A, right? Let's give that thing, that law a number. We'll call it number 10. And so by property 10, this is, we can just plug in. So this is 8 to the 1/3. And this is 9/18 minus 9 is 9 by property 10, which is easily seen to be 18. 18 as predicted by Joanna a long time ago. Thank you. There it is. So here, because we're just learning about limits, we are justifying every single step. We are justifying every single step according to the limit laws. So have fun with that. tonight, this afternoon, tomorrow. And we'll pick this up again on Wednesday. Thank you for coming. Any questions? Why can't we submit for X right from the start? Well, I mean, again, if you did that, you get the same answer. But here we're justifying why that's a possibility, why you're allowed to do that. And it's through these limit laws that you understand that this can be done. Will the midterm be a mix of pre-cal and cal? Exactly that. Yes, it will. Is this still practice from 2.1? I want to say 2.2, maybe even 2.3. It's page 102. If you look at limit laws is the thing you want to be looking out for if you're using a different book or different edition. Limit laws, every book refers to them as that. Is there web work? There is web work. Web work is up, right? Have a look at that. And I will see you guys on Wednesday. Thank you all for coming. You guys have a good one.